Hi, I'm Killian Muldoon. I'm a software engineer in Intel's network platform group. I mainly work on implementing infrastructure needed to bring kind of high performance networking applications, networking workloads to Kubernetes.
Hi, I'm Tom Golway from Hewlett Packard Enterprise, and I work in the advanced R&D organization where I'm focused on ways to provide infrastructure that supports disaggregated application architectures. Today, Killian and I will be discussing the need for a greater awareness of infrastructure capabilities in the scheduling process to look to achieve predictable service level guarantees for applications. Digital disruption and digital transformation have been viral topics for quite some time. How many times have you heard a CEO say, we don't think ourselves as a bank or whatever, we think of ourselves as a technology company. But those same companies are evolving their business models and processes much in the same way as they always have done. But we do see a shift in that. We're seeing innovation at the business level becoming more digitally aware, and their thought progression is assuming that computing with definable service levels will be both ubiquitous and pervasive. As enterprises innovate on the business side, we see a shift towards cloud native and microservice architectures. This is going to be changing the way IT resources consumed and the expectations of service levels for applications. The shift in application architecture is leading us to look at building the underlying infrastructure to support what I call infrastructure plasticity. Now that means delivering the infrastructure model that's presenting itself to applications with the capability of undergoing organic changes on the fly based on the application's class of service. So think about anything from system level changes to large scale network topological remappings. Now data is key, and the where and how data is consumed is changing. So let's take a look at that. System of record traditionally is where you are recording what has happened. Applications are typically architected either monolithic or using some simple client-server paradigms. If you look at data volumes, we typically see, let's say, a typical retail database with all historic transactions is roughly around 40 petabytes. System of engagement is about highly interactive, near real-time applications, typically handling what you would call messy data, such as social media, for example. Now, this enables companies to create new and innovative ways to deliver products and services, collect and analyze user data, use that data to create new value more relevant to their customers. Application architectures are more complex, with some levels of distribution of compute, though data tends to gravitate to centralized databases and large data lakes. If you look at data volumes, a typical per day posting of social media is about 4 petabytes. System of action supports more autonomy within the systems, either augmenting human decisions or fully controlling actions and outcomes. Processing is in real time, highly sensitive to latency and jitter, and needs high accuracy and traceability. Examples would be like a smart grid or autonomous vehicles, which generate about 4 petabytes per day per car. Application architectures are highly distributed, where compute moves to the point where data is ingested to support greater real-time execution. Compute needs to be both pervasive and contextually aware. Now, as these models are driven by evolving business requirements, so does the need to increase the performance and support higher application class of service with tighter control over the variation of service. According to IDC, the volume of data created is doubling every 2 years. That growth challenges the conventional ways that we currently build and deliver solutions. The variety of data is changing as well, with a heterogeneous mix of data types and both structured and unstructured formats. A big reason for this growth is due to the increased number of sources where data is created and ingested into the application ecosystem. Think about the proliferation of IoT with its unique data models and contextual significance. Usage of the data changes as more diverse sets of data are introduced, each potentially with having unique rates of decay. The value of the data changes directly with respect to its rate of decay. So if the higher rate of decay, the more emphasis on producing actionable outcomes in real time. Data has gravity, which is influencing where compute needs to be located. Ephemeral contextual data tends to exert the greatest gravity, typically pulling compute to the source. Data that is persistent and has broad applications with a low rate of decay tends to have the low gravity and tends to move where the compute is located. With cloud-native application architectures and distributed data sources, the veracity of data is a significant challenge. We see an increased need for trust in the data, with a focus on protection of data both in motion and at rest. But we're also seeing a trend towards protection of data in use. Application architectures are shifting towards a more disaggregated model, offering greater agility, supporting elasticity, and providing greater control for software quality assurance. By leveraging a scale-out disaggregated model, applications have the ability to be deployed using a composable model with a mix of core code, libraries, open source, external applications, and microservices. But the individual components of the application will be executed on the platform that best fits its function given the context of the overall class of service. The benefits of this are substantial. However, it brings a lot of challenges. Application topologies and flows will have greater complexity, ranging from tree structures to more complex distributed mesh. And there's a greater potential for increased latency, jitter, and traffic flow. Small degradations in performance may seem inconsequential for an individual microservice, but when aggregated to the application level, it'll impact business process service levels. And not all applications are equal, so supporting differentiated service levels are required to support the digitally aware enterprise. The expectations of the digitally aware enterprise is that as we move towards a cloud-native architecture, service metrics like performance, latency, and jitter will need to be improved while supporting application class of service guarantees. So now I'm going to turn it over to Killian, who will discuss how we support the mapping of application class of service to the infrastructure capabilities and by using Topology Aware Scheduling.
Thanks. As Tom was saying there, we're starting to get a good picture of what applications will need, and we're getting new ways to express that, but we're still falling really short on the hardware side. Kubernetes, from the orchestration level, it knows what infrastructure is made of, but it doesn't know what it can actually do, right? So the scheduler can take requests for a number of CPU cores, but it doesn't actually know or it doesn't care about how much processing an individual core can do. Memory topology, which is a complete blocker for truly predictable performance in workloads, it's not understood by the control plane, understood by the scheduler at all. So the work that, of trying to figure out what a platform is actually able to do, what the hardware is able to do, is pushed to kind of cluster operators, and sometimes even worse, it can be application developers that end up doing this work, right? This really doesn't scale well. It leaves us with kind of secret recipe configuration files in weird directories that only ever get understood by a couple of people in the organization, and kind of can lead to gatekeeping issues, but just overall just organizational issues, right? Communications issues. So Tom laid out there kind of a way to express what applications might need, and we need to match that by providing a way to describe hardware in terms applications can really understand, right? So meet them on applications terms rather than expressing hardware as a bunch of ones and zeros. So I'm mostly talking about packet processing workloads. They have intense performance characteristics. Configs get really complicated as a result, and this can be really, really hard to manage. So here on the left-hand side at the bottom under pod requirements, there's just a kind of a model spec for resource requests. There's a load of different resources in there, CPUs, virtual functions, specific speeds in there, specific power headroom needed, and there's NUMA alignment needed as well, something Kubernetes just can't do right now, even though it has massive performance impact. So we can reduce the spec if we build in kind of hardware knowledge into a traits model that matches the application model that Tom was talking about. And you can match the requirements an application has here, fast networking, maybe some encryption acceleration, power needs, whatever it is, and express that as a single trait. So in order to actually make this work, we kind of need two components. So one of those is a node trait discovery agent, which is able to actually describe platforms in terms of their capabilities. And then you need a matching engine, which is able to do the actual matching work between the application expression and the platform expression to find out what platform can actually meet the class of service required by a specific application. So here we have a kind of a prototype working of this. So it used Prometheus in order to set up rules and do the node trait discovery part of this. And then Telemetry Aware Scheduling is able to match the workloads requirements to the Prometheus expression of the trait. So when we describe platforms in terms of capabilities, you get to push a lot of the complexity of hardware configurations to a level where you can share it in kind of a consumable way across organizations, publicly even. It allows upgrades to be made. So the same application can be deployed multiple times at multiple class of service expressions. So different versions of the application actually provide different service level assurances, maybe. Different speeds in terms of packet processing, it could be. So you can actually control what level of performance is being offered to a specific application. The most important part of this, though, is you get to keep application developers away from hardware. They don't have to learn about different CPUs. They don't have to learn about the wattage of platforms, cooling. None of that hardware specific needs to be in a pod spec if you get to this capability expression. So this is kind of a proof of concept of this, but there are a bunch of caveats that will keep it from being a true working system. Really importantly here, this does kind of an ad hoc management of all the complexity of NUMA topology management of memory. All the scheduling for NUMA topology is done in Prometheus rules and in Telemetry Aware Scheduling. And even though that's absolutely necessary for predictable performance, it's not going to be scalable across all sorts of different hardware to be doing that through PromQL queries. So the question is, how do we actually get this up and running? So here we're looking at a dashboard. This is Grafana on the left-hand side and terminal windows on the right-hand side. The top three boxes here, you can see the names of the nodes, master 1, node 1, node 2. They're an indicator of the actual trait that we're working with. So that's the 10 gigabit networking at 1 million packets per second. We can see that they're all red. That means no surprise that they're in negative, right? They're in -1 as well. That means that they're not currently advertising that trait to the cluster. We can see the reason for that as well just below. So this is the power headroom. We know from looking at the trait that power headroom is actually an important part of it. You need 150 watts available in order to run this kind of workload according to our spec. So we can't actually place on any of those nodes. So this is because we have kind of power hungry workloads across the cluster. So on the right hand side in our terminal, I'm going to start the cloud function and I'm going to watch its progress through the cluster. And then on the bottom right are the logs out of the Telemetry Aware Scheduling system. So down there you will see the actual decision being made in real time by the scheduler based on these traits. So a bunch of logs are after popping up there at the bottom right. You can see for each node, so master 1, node 2, Telemetry Aware Scheduling is aware that the node is actually violating a rule, and that rule is the name of our trait. It's 10 gigabit networking at 1 million packets per second. So again, this is because we don't have enough power headroom on the system. Telemetry Aware Scheduling would continually, as the normal Kubernetes scheduler, the default scheduler does, continually retry this scheduling with a backoff. But we're not going to wait for the power to actually come back. We're not going to wait for that workload to finish. We're just going to manually preempt the workload. So this is just deleting the pod. So that's a power hungry application is going down, and we're just back watching on our cloud network function again. So that workload's going to take a minute to spin down. So while we do that, we can have a look at some of the complexity that's actually being buried here. So in this text box, There's no need to read all of this. You can see the actual makeup of a single query that satisfies this trait. This is the definition of that trait. So we have just setting min and max values, so it's plus minus 1. We check what free CPUs are there, so which ones aren't being currently used by pods, and that they're NUMA aligned, so this is free CPUs per NUMA node. We check for the CPU frequency, again per NUMA node. Huge pages, power headroom, which is the important one here. We can check for number of devices. This is our virtual functions, our network devices. Check that enough bandwidth is actually available on those devices. And then at the bottom, we're just adding a negative score for the missing nodes, because this is a filter effectively. But we want to make sure that we have -1s for the nodes that don't meet the trait as well. You can see down below, our power has actually come back. So after descheduling that power hungry application, our indicator is now green. So in a couple of minutes, hopefully a few seconds, Telemetry Aware Scheduling will once again try to schedule our networking workload. So this is our cloud network function. We can see it's in pending at the top right, but we actually have a node to place it on now. So our query there, our Prometheus query, is doing a few things that a normal scheduler can't do at all. One is it's looking at live contention, which is what we have with our power. And the second thing is it's doing NUMA alignment. Currently there's no NUMA alignment, that's memory topology in Kubernetes at the control plane level. There is the Topology Manager at the node level. So our workload has just been scheduled, judging by the top right, so it's up and running. We can see at the bottom right, the last line of our logs there is that the filtered nodes for our hardware traits, master 1, so that node has now been, that pod has now been scheduled on node 1. So just to show it up and running, we're going to just run from the host. We're just going to run a packet processing workload on it, and we'll be able to see some of the packets coming through. This is a user space DBDK workload, so it's actually avoiding the kernel in order to get really high packet rates in and out. So we use SRI VNix and all of that. So we'll see the workload on the third dial here at the bottom. We get to show packet throughput. So all of these components are available. They're all open source, and there's a document on the Telemetry Aware Scheduling repo with the collateral for this demo and showing you how to set it up and implement it. And we can see there, as the packet rate increases, the trait indicator again turns to -1, turns to red, and that means that no workloads will actually be scheduled and consume that bandwidth. So Tom put forward new ways to think about application requirements in terms of a class of service model. And we've shown here that it's actually possible to meet that on the other side by generating kind of hardware traits and then matching them off of each other. So the really kind of complex requirements that you get in performance intensive applications, right now you get loads of node labels, you get nodes that have specific resources tainted, you get big long lists of resources, all this complicated cluster management. With more accelerators, more types of processors, you know, people are talking about the era of the XPU, right, which is where you're going to have multiple different processing units in a machine. This is going to create more and more configuration overhead, right? You got more room for error, more resources locked up in just kind of managing these recipes to get your workload the performance that it requires. Just have this kind of spaghetti YAML building up over time. So even though it's complicated, this predictable performance is going to be incredibly important to getting certain workloads to work in Kubernetes. Network packet processing is one of those. Also high performance computing workloads. The configs that you're getting now, they're causing real trouble today, and they're only going to get more complicated over time. It's going to be more taxing, it's going to be more work. So the matching that we've shown here, which is kind of application class of service to live platform traits, it's one way to hurdle this obstacle, right? But there's a huge amount of work left to be done. What we've shown here today isn't going to be deployed on production anytime soon. So there's a few things really missing in Kubernetes that just cause pain. So memory topology management, major roadblock, seen that throughout this. There are kind of efforts going on through the SIG-Node resource management group to help fix these issues. We're looking forward to seeing the solutions come out of those discussions, and we hope that we'll get support for those at the kubelet and at the scheduling level. Maybe elsewhere in the control plane as well if it needs to go into the API or something like that. But the bottom line is, if we don't want developers and cluster administrators and whoever else to have to add kind of hardware engineering skills to their skill set, we need to change the way that we think about scheduling, the way we're going to match applications to hardware. This is a first step down the road, but in order to move further, we're going to need changes into Kubernetes. And I think Tom and I are around to take questions now, if anybody has anything.